The last thing we need to discuss in this lecture is removing outliers. So when you do any experiment, you usually repeat the experiment so many times and you get so many different data points. So when you do get different points or you do get different results, these results will never be exactly the same. They will always be different because we know that there will always be random error. But sometimes there might be some systematic errors and you look at one of your values and it looks like an outlier and you don't know if it's actually an outlier and there was some sort of systematic error you're not aware of or if it's just a normal random error. So there is a specific test we need to do, a specific calculation we can do in order to decide whether this one is an outlier or not. The test we run is called the Grubb's test. So the Grubb's test allow us to govern or allow us to actually judge whether a certain value is an outlier or not. Let's have an example and see. So if we measure the mass loss from two galvanized nails and we ended up with two different values. The mass loss was so many different ones, as you see here, these different values. All of them seems to be very close to each other except for this value, which is 7.8. It seems a bit far. So normally with your normal judgment, you would say 7.8, it looks like an outlier. It's a bit far from all of the values. But we cannot judge it like this. What we need to do is to run the Grubb's test. So in the Grubb's test, the first thing we need to calculate is the mean of all the 12 measurement and the standard deviation. So I need to calculate the mean and the standard deviation. And then I start to calculate G. G is the Grubb's test. So G will equal the questionable value minus the mean divided by the standard deviation. So now the questionable value for me is 7.8 because it looks like an outlier. So I put this value minus the mean divided by the standard deviation and I find my answer. So my answer here, G calculated, is 2.13. And in the same way as we looked at the T from the table, there is a table also for the G value at 95% confidence interval. So 95% confidence level. So I look the G value from the table at 95% confidence for a number of observation. Here, there is no degree of freedom. I look at the number of observations. So my total number of observations were 12. So I look it at 12. So the value opposite to the 12 number of observation is 2.285. If I look again at my calculated G will equal 2.13. Remember, when I do this, I use the absolute value for the difference between the questionable value and the mean, because it can be plus or minus. So I need to use the absolute value. I need to use it with always as a plus. And then I compare the G calculated with the G from the table. The G from the table was 2.28 and the one calculated is 2.13. So the one calculated is smaller than the G from the table. That means that I can retain this value. The difference here is due to random error. It's not due to systematic error, so I can retain it. If I calculated the G value and I found that the G is actually far or is higher than the G from the table for my number of observations, not degree of freedom, then in this case, I will discard this data and I will consider it as an outlier.